Hello and welcome to the last lecture in Module 4, which is Signals and Noise. So we have 6 objectives here, which is to identify the major types of noise and their physical origins, define signal-to-noise ratio, and so on. We also have this outline of today's lecture where we'll go through all of those, and we'll have a capstone worked example, which will try to lock in how electronics really matter in this course and beyond. Okay. So we have been dealing with the complete signal chain so far, and this is where we're at. So noise can pretty much enter at every single step that we've covered, and we've covered a lot of steps so far, and we've gotten through from the sample to the computer. We want to look at the red arrows. This is where the noise is entering, the kind of thermal noise of the transducer, amplifier noise of the op-amp, interference is picked up by the cables, quantization noise from the ADC. We've been analyzing each stage as if the signal were clean, but it's never really clean. So today we'll learn how to fight the noise systematically at each stage using the right technique for each noise type. And at the end, we'll see how all these pieces can come together in a real regulatory measurement. Okay, so what is noise? Noise is anything in the measured signal that isn't analytical and isn't a signal of interest. That's a broad definition because it's pretty much context dependent. The 60 hertz power line is noise to a chemist. It's the signal to an electrician. The consequences of noise are serious. It limits your detection limits. Remember back in module 1, when we were considering the limit of detection, which was defined as 3 times the standard deviation of the blank, divided by the slope. So noise is that standard deviation of the blank, okay? So that's where we're building from. So this is going to be something we have to consider. It's going to reduce our precision. It's going to cause errors in peak integration and obscure weak features. But we do have a key distinction here, systematic error versus random error. Systematic error, such as bias, is always in the same direction. We handle it with the calibration, which we saw back in module 1. Random error, however, is noise and it fluctuates around the true value. And we can handle it with the techniques we're learning today, which is averaging, filtering, and modulation. Okay, so we have 5 main noise types. Okay, and here they are. We have thermal, we have shot, we have flicker, and we have environmental and quantization. Okay, so they all have a physical origin, a characteristic frequency behavior, and a domain where it dominates. So Johnson noise, also called thermal noise, comes from the random motion of electrons in any resistor at finite temperature. Its spectrum is flat, and we call it white noise. The formula at the bottom left tells us it scales with the square root of 4 times Boltzmann constant times temperature times resistance times bandwidth. Okay. So shot noise then comes from the discrete nature of current carriers. When current flows, it's actually individual electrons or photons arriving at random times. Counting statistics give Poisson distribution, and the shot noise formula shows it scales with the square root of current times bandwidth. Flicker noise then or 1 over F noise comes from surface effects in semiconductors. It dominates at low frequencies, which is why DC measurements are especially noisy. Environmental noise is everything picked up from the surroundings. Power lines at 60 hertz and harmonics, RF from wireless devices, mechanical vibrations. This noise is at specific frequencies. And quantization noise, which we saw back in lecture 3, is the rounding error from the ADC. So we have to look, of course, and consider our key observation here, which is that both Johnson and shot noise formulas contain delta F, the bandwidth. The narrower the bandwidth, it equals less noise, which is why filters are designed in module 2, or sorry, in lecture 2, which will improve the signal-to-noise ratio. Okay. So noise in the frequency domain. So this is one of the most important diagrams in all of instrumentation. It shows noise power plotted against frequency on log axis. The red line falling from upper left to lower right is flicker noise. It dominates below a certain corner frequency, typically a few hertz to a few kilohertz, depending on the component. The blue flat line is a white noise, thermal plus shot. It's constant across frequency, and this is the fundamental noise floor. The orange dots are power line harmonics, 60 hertz, 120, 1/3, 180, 240, which are all related to AC power lines. These are narrow spikes at very specific frequencies. The purple dots are RF interference from wireless devices, switching power supplies, nearby equipment, which is also at specific frequencies. The design insight at the bottom gives us something powerful. Many analytical methods deliberately modulate the signal into a mid-frequency band where only white noise is present. They then avoid the low-frequency region where flicker dominates, and they avoid the specific frequencies of power lines and RF. And this is the entire philosophy behind lock-in amplification, which we'll cover shortly. Okay, so let's define signal to noise ratio first of all, okay? So signal to noise is simply the ratio of the signal to the noise, specifically the main signal amplitude divided by the standard deviation of the noise. It's often expressed in decibels as 20 log of the ratio. On the right, you see a chromatographic style peak on a noisy baseline. S is the peak height above the baseline. N is the standard deviation of the baseline fluctuations, not the peak-to-peak noise, but the standard deviation. So the rules of thumb for this, for interpreting signal to noise, is that at least 3 and a peak is detectable. That's the LOD criterion. At least 10 and it's quantifiable, the LOQ. 100 or more is routine quantitative work. 1,000 or more is high precision research. These numbers should feel familiar. LOD equals 3 times sigma from module 1 is literally a minimum signal to noise ratio of 3. Module 1 and 4 are talking about the same thing, but from different angles. So how do we avoid this? How do we reduce the noise? So we have a number of strategies, and one is the hardware strategy. There are 5 hardware strategies for noise reduction. Shielding is the first, which means blocking external electromagnetic fields. A Faraday cage around sensitive electronics, coaxial cables with grounded shields, metal enclosures. This is why instruments have metal chassis, not plastic. Grounding is the second one, and it seems pretty simple, but is subtle. Bad grounding creates ground loops where current flows between ground points at different potentials, generating 60 Hz interference. The solution is a single point or star grounding. All grounds connect to one common point, and you separate analog grounds from digital grounds because digital switching creates noise on the ground line. Low noise components. So metal film resistors are much quieter than carbon composition. Low noise op amps, cooled detectors. Remember Johnson noise scales with square root of temperature, so cooling reduces it, which is why high-end spectrophotometers have Peltier cooled or even liquid nitrogen cooled detectors. Bandwidth limitations here, so narrow bandwidth means that less noise. Use only as much bandwidth as the signal requires. This is exactly what the low-pass filter from the second lecture does. And modulation or chopping. Shift the signal away from the DC region where flicker noise dominates. FTIR spectrometers do this naturally through their continuous moving mirror. Atomic absorption instruments use metal choppers. This sets up lock-in detection. Signal averaging. So now the software side, which happens after the ADC. Signal averaging is the single most powerful noise reduction technique in analytical chemistry. The fundamental result is that if you average n independent measurements of the same signal, signal to noise ratio improves by the square root of n, not n. Square root of n. Why square root? Because signal adds coherently. Every measurement has the same true value, so n measurements sum to n times the signal. But random noise adds incoherently. The random variations partially cancel, so total noise grows only as square root of n. The ratio improves as square root of n. The plot on the right illustrates the diminishing returns. To double S over n, you need 4 averages. To get 10 times, you need 100 averages. To get 100 times, you need 10,000 averages. This is why NMR experiments can take hours to days. You're trying to get signal-to-noise improvements of 1,000 or more, which gives us a sort of a common instrument practice where FTIR typically averages 16 or 64 scans. NMR can average hundreds of thousands of scans for difficult experiments. Atomic absorption spectroscopy typically uses 3 to 5 replicates for routine analysis. Okay, so if I have a signal to noise ratio of 5 and I need a signal to noise ratio of 25, how many averages do I need? The answer would be 25, since improvement factor squared equals n. 5-fold improvement needs 25 averages. Other software techniques include digital filtering applied after the ADC. Moving average is the simplest, just replacing each point with the average of its neighbors. Savatsky-Golay is more sophisticated. It fits a polynomial over a sliding window, and this preserves peak shapes better than simple averaging, which tends to broaden peaks. Fourier filtering transforms the data to the frequency domain, zeroes out the noise bands, and transforms back, which is very powerful for periodic interference. Wavelet denoising is even more sophisticated. The key trade-off here is that the wider window gives more noise reduction but broadens space. The rule of thumb is that Savitsky-Golay window should be about a quarter to a half of the peak full width at half maximum. That balances noise reduction against resolution preservation. And the critical caveat is that digital filtering is no substitute for good hardware. One signal is lost to noise, no algorithm can fix it. Right. So lock-in amplification, what is it? So lock-in amplification is one of the most elegant techniques in instrumentation. Here's the concept. The problem is that you've got a tiny DC signal, but the DC region is full of flicker, noise, and drift. Amplifying it boosts signal and noise equally. The lock-in solution has 4 steps. First, modulate the signal, which means chopping the light beam in a spectrophotometer, or modulating the source wavelength, or rotating a polarizer. Something that moves the signal from the DC up to a chosen reference frequency, typically a few hundred hertz to a few kilohertz. Second, bandpass filter narrowly around the reference frequency. This is our filter design from lecture 2, but it's a very narrow passband. The third is, and the relatively clever part, is the phase-sensitive detection. Multiply the filtered signal by the reference waveform, then low-pass filter the product. Then math works out so that you only signal components at exactly the reference frequency and exactly in phase with the reference to produce DC output. Everything else averages to 0. The fourth is the result is a DC voltage proportional to the amplitude of the signal at the reference frequency. You've extracted it from the arbitrarily high noise. Okay, so lock-in amplifiers can achieve effective bandwidths below 0.01 hertz. That's equivalent to averaging for 100 seconds per sample. So signal-to-noise improvements of 1,000 or to 1,000,000 are routine. It's typically used in AAS for lamp modulation, fluorescence, EPR, and many research instruments. Okay, so now we're going to move on to our capstone worked example. So here we have a big problem, okay? Where we're putting all 4 modules together. So this is going to occupy the rest of the lecture, and it's designed to take all of the components from each one of the different modules we've done and try to show how they can be combined together. So this is a real problem. A laboratory or regulatory lab must verify that drinking water contains less than 10 parts per billion of lead. That's the Philippine FDA limit. And so we have a graphite furnace atomic absorption spectrometer. And so we want to design the measurement workflow showing how each module contributes. This diagram shows how that happens in the workflow here. So we'll trace the lead atoms from the water sample all the way to the reported concentration and use every module along the way. Okay, so step 1, it comes from module 3 on AAS, an atomic spectrophotometry. So why do we use GFAS for this application? So lead is a metal with a strong atomic absorption line of 283.3 nanometers. GFAS has a detection limit of lead for about 0.05 ppb. That's 200 times below our 10 ppb limit, which is plenty of space. FAS, by contrast, has a LOD of about 20 ppb, which is no use for us. MCP-MS could work, but it's more expensive and a little bit unnecessary. So the instrument parameters are, of course, we have our hollow cathode lamp for lead at 283.3 nanometers. The graphite furnace runs in a 3-step program: dry at 110 degrees Celsius to remove water, char at 850 to remove the organic matrix, atomize at 1800 to vaporize the lead, argon purge gas protects the graphite, of course, from oxidation, and deuterium background correction handles the broadband furnace emission. Okay, so what are we applying here for module 3? So we're selecting the correct atomic spectroscopic technique based on limited detection requirements. And so that's what we learned about in module 3. Okay. The next step is to trace the signal from the lead atoms to voltage. So this is going to be using module 4 or the electronics module lectures 1 and 2. So first, the sample excitation. So lead atoms in the graphite furnace absorb light from the hollow cathode lamp. Less light reaches the detector when lead is present. The transducer from lecture 1 is a PMT. The PMT converts photons to current. In our example, the blank with full lamp intensity produces about 2 microamps of photocurrent. At 10 ppb lead, the photocurrent drops to about 0.5 microamps because lead atoms are absorbing some of the light. The transimpedance amplifier from lecture 2 converts the current to voltage. We chose R sub F equals 1 mega ohm, which the blank gives 2 volts out. So the 10 ppb sample gives about 0.5 volts out. And we calculate absorbance the way we did in module 2. log of V blank divided by V sample, log of 2 divided by 0.5 equals log of 4, which is 0.602 absorbance units. Okay, so we've applied several concepts from electronics lectures 1 and 2. Okay, the next one is dealing with the noise. So here in the case of the noise, we want to manage the noise, which is coming from our electronics lecture 2 and 4. So the major noise sources in GFAS are the PMT shot noise, which of course scales with the square root of photon flux, the lamp flicker noise dominating below 10 Hertz, 60 Hertz power line interference, and furnace emission during atomization, which produces broadband light that overlaps the analyte signal. So our strategy here is using 5 techniques. We first modulate the lamp at 300 Hertz, which mechanically chops or electronically pulses. This shifts our signal from DC up to 300 Hertz out of the flicker noise region. Second is the bandpass filter at 300 Hertz with plus or minus 10 Hertz bandwidth. This rejects the 60 Hertz in line noise and most of the flicker noise. Third is phase-sensitive detection. So we have a lock-in amplification, which demodulates back to DC, keeping only signal at exactly 300 Hertz in phase with the chopper. Fourth, signal averaging. So 3 replicate atomizations. This improves the signal-to-noise ratio by the square root of 3, which is 1.73 times. And the fifth then is deuterium background correction, which subtracts the broadband furnace emission. The D2 lamp spans the same spectral region, but is much broader than the 283.3 nanometer line, so subtracting its contribution removes the background without affecting the atomic absorption. So we've applied several concepts there from electronics lectures 2 and 4. Okay, so the next one then is digitization, so the ADC requirements for this measurement. So the dynamic range requirement. So our maximum signal is 2 volts. The minimum meaningful signal difference corresponds to about 0.25 ppb sensitivity, which translates to 50 microvolts. So the ratio is 40,000 to 1, or about 82 decibels. To cover 40,000 levels, we need 2 to the n greater than or equal to 40,000, which means that at least 16 bits are required. So a 16-bit ADC is the standard choice. For the sampling, then the atomization transient lasts about 3 seconds, with the peak of interest about 0.5 seconds wide. After the lock-in demodulation, our signal bandwidth is about 10 Hertz. Nyquist requires at least 20 Hertz sampling, so we have to make a practical choice of 100 Hertz, giving 10 times oversampling for digital filter headroom. And we put an anti-aliasing filter at about 30 Hertz before the ADC, and we look at the lecture 2 in the electronics module, low-pass filter design for that. So we've applied several concepts from lecture 3 in electronics, ADC resolution calculation, Nyquist sampling theorem, and anti-aliasing filter, which is exactly the analysis that we used in our work examples from that. Okay, so now we're going back to module 1, which is our calibration and validation. So this closes the loop. We have digital absorbance values, but they're meaningless without calibration and validation. So we use external standard calibration. So we prepare 5 lead samples, different concentrations, bracketing our 10 ppb sample, our limit. We run each in triplicate. We plot absorbance versus concentration and so on, and we get an R-squared value, which is very acceptable. Our method validation parameters also for module 1. So we look up our limit of detection as being 3 times 0.0024 divided by 0.0598, which is 0.12 ppb. The limit of detection, our limit of quantitation is 0.40 ppb. So our linear range is verified up to 40 ppb because we have our calibration. Accuracy is checked by spike recovery, and precision is also. So we applied to the water sample. So we measured the absorbance is 0.365, concentration equals 0.365 minus 0.003 divided by 0.0598, which gives us 6.05 ppb, which is within with 3.2% RSD. The uncertainty is plus or minus 0.2 ppb. Okay, so we've applied several concepts there from module 1. All right, let's put it all together. So we have used all of our previous modules, including the current electronics module, and we've reported a result which is compliant with the Philippine FDA, okay? So why is this important? So each module plays a distinct role in every analytical measurement. So for example, module 1 asks, can we trust our result? Module 2 and 3 asks, what physical principle gives us the signal? So how do we get the signal? And then module 4 asks us, how did that signal become a number? Okay, so we can use this information to diagnose problems at any stage. We can come up with solutions and we can try to fix them, or we can intelligently communicate with engineers, managers, and regulators. Okay. So key takeaways here are got different types of noise. We looked at signal to noise ratio. We looked at how everything can be integrated. We look at how we can improve things and different techniques that we have. Okay. So after that, we'll have, of course, have our assessment. So make sure to review these topics. And here are some practice problems, which are always going to call back to the assessments. And then if you've got any questions, just, let me know and we'll try to answer. Thank you.